Welcome to the workshop. In today's video, we restore a heavy-duty truck driveshaft from start to finish. Watch the complete process including inspection, cleaning, rust removal, straightness check, yoke repair, U-joint replacement, welding, precision machining, dynamic balancing, painting, lubrication, and final assembly. Learn how a worn driveshaft is brought back to reliable working condition for heavy commercial vehicles. Bearing journal dimensions and yoke alignment. Every measurement is documented because accuracy during restoration is essential for smooth operation after installation. Once the inspection is complete, the mechanics mark the orientation of every component using paint markers or center punches. These alignment marks ensure that the driveshaft can be reassembled in its original phase if reusable parts remain. Incorrect phasing changes the operating angles of the universal joints and creates severe vibration, even if all components are new. Maintaining correct alignment is one of the most important steps during driveshaft rebuilding. The disassembly process now begins. Snap rings retaining the universal joint bearing caps are removed using specialized snap ring pliers. Some snap rings are heavily corroded and require penetrating oil before removal. If rust has locked them into place, gentle tapping with a brass punch helps free the rings without damaging the yoke. After removing the snap rings, the driveshaft is transferred to a hydraulic press. Steady pressure is applied to push the bearing caps from the yoke. Care is taken to support the yoke correctly to prevent bending or cracking during pressing. Once the bearing caps move free, the universal joint cross is removed. Each bearing cap is inspected for signs of needle bearing failure, discoloration from overheating, water contamination, or lack of lubrication. Missing needle bearings, broken seals, or metal debris confirm that replacement is necessary. Heavy-duty driveshafts are large, heavy components that require proper lifting techniques and suitable equipment. Mechanics wear safety glasses, gloves, protective footwear, and hearing protection whenever grinding or machining operations are performed. The work area is cleaned and organized to prevent accidents and to ensure that all removed parts are stored in order for reassembly. Once the driveshaft is placed securely on the workbench, the restoration begins with a detailed visual inspection. The mechanics slowly rotate the shaft while examining its entire length. Every weld seam is checked for cracks or signs of previous repairs. The steel tube is inspected for dents, bends, impact damage, corrosion, and excessive rust. Even a small dent can upset the balance of a driveshaft rotating at high speed, creating damaging vibrations throughout the vehicle. The yokes at both ends are examined carefully for distortion, damaged bearing cap seats, worn ears, and cracks. The universal joints are tested by hand to check for stiffness. The driveshaft is mounted securely in the chuck. A dial indicator is used to check runout and ensure that the shaft rotates concentrically. Any excessive runout is corrected before machining begins. This setup stage is extremely important because even a slight misalignment can affect the final balance of the driveshaft. The operator selects the proper spindle speed based on the material, shaft diameter, and cutting tool. Feed rate and depth of cut are also adjusted according to the machining requirements. Heavy cuts are avoided during precision work because they can introduce vibration and excessive heat. Before switching on the machine, the operator wears appropriate personal protective equipment, including safety glasses, hearing protection, and close-fitting clothing. Loose sleeves, gloves near rotating parts, jewelry, and long hair must be secured because they can become caught in the rotating shaft. The lathe is started at a low speed to verify that the workpiece rotates smoothly without excessive vibration. Once everything is confirmed, the cutting tool is slowly advanced toward the rotating driveshaft using the carriage handwheel. The first light cut removes the outer surface and establishes a clean machining reference. As the tool moves along the shaft, it removes material in a continuous spiral chip. Cutting fluid is applied to reduce heat, improve surface finish, and extend tool life. The operator carefully monitors chip formation, cutting sound, and tool condition throughout the process. Smooth, continuous chips usually indicate stable cutting conditions, while excessive chatter or discoloration may indicate incorrect cutting parameters. Multiple light passes are made instead of one heavy cut. After each pass, the diameter is measured using a micrometer. Precision measurement is essential because drive shafts often require tight dimensional tolerances. The operator gradually approaches the final size while maintaining an excellent surface finish. During the drive shaft restoration process, one of the most important machining operations is removing extra metal from the surface of the shaft. This operation is performed on a precision lathe machine to restore the correct diameter, remove damaged material, eliminate corrosion, and prepare the shaft for balancing or further repairs. Before machining begins, the technician carefully measures the drive shaft using a micrometer, vernier caliper, and dial indicator. Every measurement is compared with the manufacturer's specifications to determine exactly how much material must be removed. The goal is never to remove unnecessary metal, but only the damaged or excess material while maintaining the shaft's original strength and dimensional accuracy. The shaft is thoroughly cleaned to remove grease, rust, dirt, and old paint so that accurate measurements can be taken. Any cracks, deep scratches, dents, or bent areas are identified before the machining process begins. If serious cracks are found, the shaft is replaced rather than machined because structural damage cannot be safely repaired by simply removing metal. The drive shaft is then mounted securely in the lathe chuck. For long shafts, the opposite end is supported by the tailstock center or a steady rest to prevent vibration during rotation. Proper alignment is checked with a dial indicator to ensure that the shaft runs true with minimum runout. Accurate alignment is essential because even a small amount of misalignment can cause uneven cutting and result in an unbalanced drive shaft. Once the shaft is centered, the cutting tool is installed in the tool post. A carbide insert tool is generally preferred because it produces excellent surface finishes, withstands high cutting temperatures, and maintains a sharp cutting edge for a long time. The cutting tool is adjusted precisely to the center height of the rotating shaft. Incorrect tool height can cause poor cutting action, excessive tool wear, chatter. Drive shaft has been cut and the extra metal has been removed on the lathe machine. The next stage is welding and grinding. This is one of the most critical steps in the restoration process because the drive shaft rotates at high speed while transmitting engine torque to the differential. Any mistake during welding or grinding can cause vibration, poor balance, premature bearing wear, universal joint failure, and even complete drive shaft failure. For this reason, every stage must be carried out with precision, patience, and strict safety procedures. The first step is preparing the welding area. The machined surfaces are cleaned thoroughly to remove grease, oil, rust, paint, and dirt. A clean metal surface is essential because contaminants can create porosity, weak welds, and poor fusion. A wire brush, grinder, and cleaning solvent are used to expose bright, clean steel. The technician carefully inspects the shaft for hidden cracks or defects before welding begins. If major cracks extend deep into the shaft, the component should be replaced instead of repaired because structural integrity is the highest priority. After cleaning, the ends of the shaft are prepared with a proper bevel. The bevel allows deeper weld penetration and creates a stronger joint. The angle and depth of the bevel depend on the shaft thickness and welding procedure. Once the bevel is complete, both sections of the drive shaft are aligned carefully using a fixture or alignment jig. Accurate alignment is extremely important because even a slight offset can produce excessive runout and vibration during vehicle operation. The technician checks straightness using a dial indicator before any welding takes place. The welding machine is then prepared. Depending on the workshop, MIG welding, TIG welding, or stick welding may be used. MIG welding is commonly chosen because it provides excellent penetration, high productivity, and consistent weld quality. The welding voltage, wire feed speed, and shielding. The machining work has been completed. The damaged section has been removed. The replacement piece has been prepared, and both ends of the drive shaft have been aligned with precision. Now we have reached one of the most critical stages of the entire restoration process, the final welding. This operation determines the overall strength, durability, and reliability of the repaired drive shaft. Since a drive shaft rotates at very high speeds while transmitting engine power from the transmission to the differential, the weld must be strong, straight, and free from defects. Even a slight misalignment or poor quality weld can lead to vibration, noise, premature wear of universal joints, bearing damage, and possible drivetrain failure. For this reason, the final welding process is performed slowly, carefully, and with complete attention to detail. Before striking the welding arc, the technician performs one last inspection. The shaft is securely held in a welding fixture that keeps both sections perfectly aligned. The centerline is checked using precision measuring tools, and the gap between the two sections is inspected to ensure it matches the welding procedure. The beveled edges are clean and free from oil, rust, paint, moisture, and grinding dust. Any contamination could weaken the weld or create porosity, so the joint is cleaned thoroughly before welding begins. The welding machine is then adjusted according to the material and wall thickness of the drive shaft. The correct voltage, current, wire feed speed, and shielding gas flow are selected to produce deep penetration without overheating the metal. A suitable filler material is chosen to match the strength and properties of the original steel. These settings are carefully verified because they directly affect weld quality and the service life of the repaired component. With everything prepared, the welder begins the final weld. The arc is started smoothly, and a stable weld pool is formed. The torch is moved around. The final welding now begins. The welding torch moves slowly around the circumference of the rotating shaft while maintaining a steady travel speed and a consistent arc length. The molten weld pool flows smoothly into the joint, creating complete fusion between the original shaft and the replacement section. Every movement is carefully controlled to produce a uniform weld bead with excellent penetration and maximum strength. Heat input is monitored continuously to prevent distortion or warping of the drive shaft. After completing the first weld pass, the technician allows the shaft to cool naturally. The weld is inspected carefully for cracks, porosity, undercut, lack of fusion, and other defects. If necessary, additional weld passes. Thank you for watching. If you enjoyed this video, please like, share, and subscribe to support the channel. Turn on the notification bell so you never miss our latest workshop restoration, machining, welding, and heavy-duty truck repair videos. We appreciate your support, and we'll see you in the next workshop project. Stay safe and keep learning.